Log on, tune in, find out. Another good idea from Cambridge.
Thank you, and thank for the invitation to speak here, my first time at Cambridge. So this is based on the master thesis of my student, Moran Klein from Tel Aviv University. So here's is there a laser pointer here?
This was one
You can read it later.
gosh, yes.
Okay, good. So the main physical motivation for this comes from nonlinear optics, the 2D.
So can you turn the mic on?
One, two, three, one. Is it okay now? How do you point?
Pointing on you now.
Aha, okay. Okay, good. So the setup is the 2D cubic NLS. It's a very common model in physics, rise in nonlinear optics, in BC, other fields. And my main interest comes from nonlinear optics. In that case, you have a laser beam. It propagates in the z direction in some homogeneous medium, air, glass, water, silica, whatever. And so this is the direction of propagation. X and Y are the transverse coordinates. And the psi is the electric field amplitude. And this equation models the propagation of the laser beam. And there is a competition here between the Laplacian, the diffraction term, which tries to make the laser beam wider with propagation, and the Kerr nonlinearity, the focusing nonlinearity, which tries to make the beam narrower with propagation. And here, z is a time-like variable, it's an evolution variable. So it's an initial value problem in z. And people have done experiments in the early 60s with high power laser. They've shown them in glass or in water. And what they saw is that if the laser beam is sufficiently powerful, it becomes narrower and narrower until it damages the material. So they call this catastrophic collapse. And this phenomena was explained in '65 by Kelly. He took the 2D cubic NLS with a Gaussian initial condition, solved it numerically, and saw that after some time, the solution essentially becomes singular. So here I write time, but you should remember that physically it's after a finite propagation distance. So this was the beginning of singular solution in the NLS of the study. And then the obvious question is what happens after the singularities? Physically, there's no singularity. The laser beam goes on. It continues to propagate. So if you have a singular solution, it means that you use an approximate model whose validity breaks down at the singularity. So what should you do? So the standard approach for continuing the solution beyond the singularity has been to say, okay, actually the NLS is only an approximate model. The correct physical model is some nonlinear Maxwell or nonlinear Helmholtz equation. So let's look on all the terms that we neglected in the process. Let's start putting them back in and see when we have global existence. And there have been tons of study of that sort. But we can think of a different approach, and the motivation comes from conservation laws. You have a similar phenomenon in conservation laws, where you also have solutions that become singular. In that case, they don't blow up, they just become shocked, the derivative become infinite. And in that case, you know that, well, you can have singular solution without viscosity. Once you put back the viscosity in, there's no singularity. But in conservation laws, there's a literature on how you continue the singular solution without having the viscosity inside. And it goes with Riemann solvers, vanishing viscosity solution, entropy condition, jump condition. There's a whole literature on just how to solve this thing numerically. There's a huge literature on this problem. So the goal of this study has been to do a similar, or to initiate a similar approach for the NLS. So what do I mean by a similar approach? Here we have again the singular solution, NLS solution. Until here the dynamics is described by the NLS. Here is the blow-up time. We want to know what's going on here, but we want to do it to continue this, to have the solution satisfy the NLS also after the singularity. So we don't want to add the viscous terms. So if we want to do it, we need somehow to know what happens here. We need some sort of a jump condition to be able to relate the solution of the NLS here to the solution of the NLS here. That's the goal. So far, there have been only 2 studies by Merle, which I'll present in a second, which address this question. Okay, so let's begin with a quick review of NLS theory, the part which is relevant for this talk. So I consider a more general NLS now. It's in D dimensions, T is time, X is in RD, and the nonlinearity exponent is 2 sigma. And the standard definition of singularity formation is that the initial condition is in H1, and if the H1 norms become infinite, we said that the solution becomes singular. So the well-known classification of NLS as far as singularity formation, sigma d less than 2 is the subcritical or L2 subcritical case. Always you have global existence, but sigma d equal to the critical case or above to the supercritical case. In both cases, you can have singular solutions. I'll mainly focus in this talk about the critical case, sigma d equal 2, mainly because it's motivated by the propagation of laser beams in bulk medium. And because of that, you can get rid of the sigma here and write the nonlinearity just as 4 over t. Okay, so you can look for standing wave solutions that propagate without changing the radial profile of the form e to the it r of r. You plug this into the NLS and you get that r is the solution of this nonlinear ODE. In 2 dimensions, actually this ODE has this boundary value problem, has infinite number of solutions, but the one we care about is the ground state, the one with the minimal L2 norm, or minimal power, and it's in 2 dimensions. It looks like this. It's sometimes in the nonlinear optics literature, it's called the Towns profile, and it's roughly like a Gaussian type solution. And Weinstein proved in '83 that a necessary condition for collapse is that the L2 norm of the initial solution would be above some number, which is exactly the L2 norm of the R profile. So this is a necessary condition for collapse in the critical NLS. And I'll call in this talk the L2 norm the power. People sometimes call this the mass, but in optics, it physically corresponds to the laser power, how many watts or megawatts the laser beam has. So from now on, this would be denoted as power, and so P critical is called the critical power for collapse. You need at least this high power in order for the solution to become singular. The R profile can also be used to construct explicit singular solution as follows. You take the R profile and you rescale the radial variable by some function L of t, which is linear in time. And then you use this L of t also to rescale the amplitude, to rescale the phase here as 1 over L square, and to add some quadratic phase term which corresponds to the focusing. And this is an exact solution of the NLS. Now, L of t, you can think of this as the width of the solution, and it goes to 0 at Tc, and therefore it means that the beam shrinks to 0 and its amplitude goes to infinity. So the solution, this explicit solution, becomes singularity C. And the blow-up rate of L of t is linear. So it looks like this triangle. If you take the absolute value of this explicit solution, you see that it's the R square function modulated by 1 over L to the D. So it has exactly the same power as the R profile. It has exactly the critical power. And it goes to a delta function exactly at the singularity. And since it has exactly the minimal power which is needed for collapse, these solutions are sometimes called minimal power blow-up solutions. And actually it was shown by Weinstein and subsequently by Merle that these are the only minimal power blow-up solutions. Any solution, a singular solution that has exactly the critical power has to be given by this explicit solution. Now, when this solution was first found, it looked like a very good thing because, well, you can start understanding what's going on with singularity formation just by looking at the solution. But it soon became clear that these solutions are not good in the sense that they are not generic. They are unstable. Why are they unstable? Because they have exactly the critical power for collapse. So any small perturbation that would reduce their power below critical would arrest the collapse. So these are non-physical, non-stable solutions. You don't see them in simulations. You don't see them in experiments. So how do the stable blow-up solution of the NLS look? So this was a problem that attracted a lot of attention during the 80s. Eventually, Freiman and independently Papanicolaou and co-workers showed that if you blow up in a stable way, you blow up with a self-similar psi R profile. So it's again the R profile modulated by this function L of D, but L of T is not linear. Rather, it goes to 0 at a square root rate with a log-log correction. So this became known as the log-log law. And it was the rigorous justification for this came a few years ago in a series of studies by Merle and Raphael. Okay, let's go back to the goal of this talk, continuation of solutions beyond the singularity. In 1992, Merle presented a beautiful paper on a continuation, and his idea was as follows. He took this explicit blow-up solution at t equals 0 and multiplied it by 1 minus epsilon. So the power of this initial condition is below critical, so it exists globally. And then he computed the limit as epsilon goes to 0 plus of this psi epsilon. Now, this is Merle, so when I say computed, I mean a rigorous computation. And here is the result. Before the singularity, for t less than tc, you just go on to the explicit solution. And this is just by continuity. Nothing surprising here. The initial condition goes to the same initial condition. So it's just this familiar thing that we saw before. The really interesting is what happens after the singularity. After the singularity, if you look on the absolute value of psi epsilon at tc plus t, it's equal to this explicit solution at tc minus t. In other words, the value here is equal to the value here. So there is a reflection or symmetry with respect to dc. Therefore, if you look on the width of the solution, it's linear both before the singularity and after the singularity. But if you want to know what happens with the phase, you don't want just the restriction of the absolute value, then it turns out that for any theta, there is some sequence epsilon n going to 0 plus, such that the limit of psi epsilon n goes to psi at tc minus t, but with some e to the I theta here. So you have the limit after the singularity up to a constant phase, which you cannot determine. So the solution is completely symmetric with respect to the singularity point, except for the phase information, which after the singularity is lost. Why is the phase information lost? Intuitively, the reason is as follows. If you look on this solution before the singularity, and you look on its on-axis phase, the phase at t equals 0, then it's the integral of L to the minus 2, and L is linear, and so this on-axis phase goes to infinity. So if at Tc it goes to infinity, after Tc it goes to infinity plus something. So you just lose the phase information. So Merle result is the only explicit continuation of NLS solutions beyond the singularity. It's a beautiful result, but it's very limited. It's only the critical NLS, and more importantly, it's only for one type of initial conditions, this explicit singular solution, which are unstable and therefore non-generic. And so the starting point for this study was the question, well, what can we say more about continuation? Can you do more? So I'll begin with a generalization of Merle's approach. So we take some initial some profile f of x in H1, any profile, and then we look on the NLS solution with the initial condition, which is k times this f of x. And now we vary the value of k. So if k is sufficiently high, you would have collapse. If it's sufficiently small, you don't have collapse. So we look for the minimal value of k for which you get collapse for the first time. And we call it k threshold. And now, once we define this k threshold, we look on this initial condition, 1 minus epsilon k threshold f of x. So by this construction, if epsilon is positive, you don't have collapse because your k is below k threshold. If epsilon is negative, your k is above k threshold, so you do have collapse. So therefore, following Merle's approach, we compute the limit of psi epsilon as epsilon goes to 0 plus. We can do it because for every positive epsilon we have global existence. And if we can do this, this would give us a continuation of this singular solution, psi tx and k threshold. Now, the computation here is a asymptotic computation. It's not a rigorous one. Let me briefly show the idea. So what we know from NLS theory is that near the singularity, as we said before, the solution collapses with this psi R profile, which is a modulated R profile. So it's for some, it's not for all t, it's for some time sufficiently close to the singularity. And using this assumption and other stuff, you can show the dynamics of L of t, the beam width, is governed by this system of ODEs. So we have here LTT is minus beta over L cubed, and beta t is this minus nu of beta over L square. Nu of beta is this exponentially small term in beta when beta is positive and 0 when beta is negative. So this is the system that was derived in the 80s by Freiman and by Papa Nicolau and co-workers. And because of this exponentially small term, if beta is positive, from this you get the log log law. But now we are in a different situation, because when we take our initial conditions, there are globally existing solutions. And therefore, you can show that this implies that beta is negative. So if you come not with a singular, but below the threshold power for collapse, beta is 0, is negative, so nu is 0. And therefore, you don't have this term which gives you the log log law. You rather have just beta equal constant, because this is 0. So there's no log log, and as epsilon goes to 0, beta goes to 0, but to 0 plus, and to 0 minus, and therefore if this goes to 0, LTT goes to 0, and so L is linear in T.
But if you are with the psi r profile, but L is linear in T, you are back to the explicit solution. So if you go below the threshold power, you do get attracted to this explicit solution. So the upshot of this is that before the singularity, you go to this explicit solution, not for all time, just from T0 to Tc. And after the singularity, for some time after the singularity, psi epsilon Tc plus T is the explicit solution at Tc minus T. So again, you have this symmetry with respect to Tc. And this implies in particular that the blow-up rate of L of T is linear before and after the singularity, not for all T, but for times close to the singularity. And what about the phase? The same as in Merle's paper. For any theta, there is a sequence epsilon n go to 0 plus, such that psi epsilon n at Tc plus T is e to the I theta psi star epsilon at Tc minus T. So again, you have the symmetry with respect to the singularity time, but you lose the phase information. And why do you lose it? For the same reason as before, because the limiting phase at the singularity is infinite. So anything after the singularity is infinity plus something, so you lose the phase information. Okay, some supporting numerical simulation. We take the 1D critical NLS, so it's 1D quintic, Gaussian initial condition. We look numerically for the value of K threshold. We find it numerically. And then we take the initial condition is 1 minus epsilon times this K threshold. We have a globally existing solution, and we compute it for epsilon going down. So epsilon 4 times 10 to the minus 5, this solution L goes to 0 but then stops. As we decrease the value of epsilon, we get closer and closer to the singular solution with the K threshold. And you can see that L of T does, you see here there's no convergence because here you're still far from the asymptotic regime where the reduced equations are valid, but roughly from here on you have a nice convergence of L of T to this linear rate, both before but also after the singularity.
How do you have the solution solid?
This is just, I plot this. I just plot this. So I see that these are numerical, and this is the theoretical prediction. And actually, I haven't shown it here, but if you take these values and do the extrapolation, you get almost a line on top of a line on this. What about the loss of phase? So the first question was, how do you observe numerically loss of phase? So the idea is as follows. We take the on-axis phase, we plot it as a function of t, for various values of epsilon, so 2, 6, 4, and 2, 10 to the minus 5. So in other words, we change the initial condition in the 5th digit. And you can see here it has absolutely no effect on the phase initially, but once you get close to the singularity, it has an order 1 effect on the phase. So 10 to the minus 5 changes in the initial conditions lead to order 1 changes in the phase after the collapse. So this is the signature of the loss of phase at epsilon goes to 0. And as we said, why is that? Because if you look just at Tc, at the singularity, the phase goes to infinity as epsilon goes to 0. So if here it goes to infinity, here you lose the phase information. Now, you can say, why should we care about the fact that we lose the phase? It's interesting mathematically, but if you take NLS solution, you multiply it by e to the I theta, it remains the same NLS solution. Multiplying initial condition by e to the I theta has absolutely no effect. So why does it matter that we lose the phase information? So the answer is that, yeah, if you have just a single beam, it doesn't really matter. But the real interesting effect is when you have two beams intersecting. So let's look to see this. Let's look on the following situation. We send two laser beams, one coming from here, one coming from here, and it's also plotted down here. And each beam has power slightly below critical. So each beam undergo focusing, but it doesn't have enough power to collapse, so it's defocusing. And we set the beam so here, they almost collapse around 0.3. And we do the setup so that later, after collapse was arrested, they would intersect. And you ask, what would happen when these two beams intersect? So in the first simulation, these two beams are identical. They have the same input power, same profile, same input phase. So they are in-phase beams. So once they intersect, together they intersect constructively. They have almost two critical powers, well above what we need for collapse. So they collapse. Now we repeat the same simulation. The two beams are still in phase, same profile. The only thing is that one beam is multiplied by 3 in the 5th digit. A tiny change in the power of the second beam. So before the collapse, it's the same. They almost collapse. Collapse is arrested. Once they intersect, however, you see there's no collapse here. There's some minor thing, but no collapse. And if you want to see why they didn't collapse, the thing to look is on the relative phase of these two beams. And if you look on the relative phase between these two beams, you see it's initially 0 because they are in phase, but around the collapse time, they accumulate a big difference, and they almost have a pi phase shift between each other. So why is this pi phase shift? Because of this high sensitivity of the post-collapse phase to infinitesimal changes in the initial condition. This loss of phase, post-collapse loss of phase phenomena. But because they now come with this pi phase shift, it has an order 1 effect on the dynamics. So what this means is that if you have two beams and they already collapsed and they interact, you cannot say what would happen with the interaction. You cannot say whether they would be in phase or out phase. It's completely chaotic. You lose the phase information. So you can only make a average statement. You can say there is a 50% chance there will be in phase, 50% out of phase, but you cannot make a deterministic statement. Okay. Now in 2005, we found a new type of singular solution of the critical NLS, which collapsed with the ring profile, not with the R profile. So here we took the 2D cubic NLS. These solutions are also, you can write them in explicit form, psi G. It's almost like the psi R, only now there is G instead of R. That's the first difference. The second difference is that L of t has a square root dependence and not linear anymore. So G is now the solution of this nonlinear ODE. It's almost the R function except the R equation except for this extra term. So here you see also the square root dependence of the beam profile. So the absolute value of this is like this. And if the G has a ring shape, this is R, this is psi G, so it has a ring shape. So you see this is a t equals 0, 1, 2, and 3. So as the solution evolves, the ring amplitude becomes higher, the widths become narrower, and it approaches the singularity, the origin. So it's like a shrinking ring or a shrinking crater that becomes narrower, higher, and closer and shrinks to the singularity. So this solution becomes singular at the origin, but not with the R profile, with the G profile. And what we say, can we do a continuation for these solutions beyond the singularity? So the obvious thing is to do the approach that we have done before, to take the play with the coefficient until we get exactly the minimal power for collapse. But this won't work here. And the reason is that if you reduce the power of these ring profiles, you ultimately go to the R profile. because to have this ring type collapse, you need many, many times the critical power for collapse. So you need a different type of a continuation. So here is one possibility for continuation. We take the origin and we add a hole here around the origin of radius r0. So we solve the NLS only for r between r0 and infinity, so outside of this hole. At the hole we put a Dirichlet boundary condition. Physically, it means you put a reflector here so that every radiation that hits the boundary is reflected outward. So this would stop the collapse. You have global existence. So let me show how the dynamics looks. Here you start with your ring. Initially it shrinks towards the origin. Here R0 is the hole location, so it becomes higher and narrower, but here it exactly hits the hole, and so it gets reflected backwards. So it starts moving backwards and expanding, going down and becoming wider. So for every positive R0, every hole, you don't have collapse. And now if you want to do the continuation, let the hole size go to 0. So now the continuation is done by playing with the domain. So before the singularity, again, it's just from a continuity argument, you see that you go to the explicit solution. But what happens after the singularity? How can we compute the solution after the singularity? Previously, we relied on the fact that we had an asymptotic theory which was developed in the 80s for the dynamics of L and beta if you are close to the R profile. There is no such asymptotic theory for ring solutions. So we need a different approach. So it turns out that you can use a very important property of the NLS, and this is the fact that the NLS is time reversal. Unlike the heat equation where it makes the whole difference in the world if T goes up or down, in Schrodinger it doesn't matter. You can let T go to minus T and psi go to psi star, and the equation remains invariant. Physically, it doesn't matter for the laser beam if it propagates in the positive z direction or in the negative z direction. It's the same physics. So therefore, if you are just here at this location where collapse was, so here is the shrinking solution, here it just stopped, it's about to move backwards. If you stand here and you move forward in time or backward in time, you should have exactly the same kind of dynamics. So the solution, this shrinking, expanding ring solution, should be symmetric with respect to the reflection time, the time when it's been reflected. Now, as the hole size goes to 0, this reflection time goes to Tc, and therefore you see that the continuation should be symmetric with respect to Tc. So in a way, this gives us the jump condition that we wanted. We wanted to know how to connect the solution before and after the singularity, so at least in this case, that's the question. The symmetry with respect to Tc is your jump condition. What about the phase? Well, as before, since the phase of this solution becomes infinite at the singularity, anything after the singularity, you cannot determine the phase. It's infinity plus something, so again, you lose the phase. So the summary of this is that if you take this continuation of ring solution with this shrinking hole approach, before the singularity you just go to the solution, so it's this. After the singularity you have this reflection with respect to Tc, so the value here is equal to the value here in the limit. But L of T now has this square root dependence before and after the singularity. And if you want to remove this absolute value, again you have that for any, well, I wrote it alpha, for any phase that you put here, you can also always find a sequence Rn of whole sizes going to 0 that you would get this solution up to this phase factor. So again, you lose the phase information after the singularity. Okay, some numerical support. So here we solve this NLS with the hole for different hole sizes. And so this is R0 0.15, 0.125, 0.1. So we do this calculation. Then we take the extrapolation of this to R equals 0. We get this profile. And we compare this extrapolation with the theoretical prediction. And they are one on top of the other. So this is the convergence of the absolute value. Here we plot the beam width, L of t, and we see that at R0 goes to 0, we converge this square root behavior before and after the singularity. And here we look on the loss of phase phenomena. So we took various hole sizes. You see it has absolutely no effect on the on-axis phase before the singularity, but around the singularity it makes a very large difference, and after the singularity the difference even increases. So basically as R0 goes to 0, you lose the phase information. And to see it here, we took the values of the phases here and we added more dots, and you can see that as R0 goes to 0, this should go to infinity. But now what we really used in making the continuation of this ring solution is just the fact that we have this time reversal property. And therefore, the conclusion is that any continuation of the NLS which would preserve the invariance under t going to minus t and psi go to psi conjugate, any continuation of like this would be symmetric with respect to Tc, and you would have the phase loss at and after the singularity. So this holds for Merle's continuation, it's time reversal. For the sub-threshold continuation that we've done, which is the generalization of Merle's approach, it also holds for the vanishing hole continuation. But it holds this time reversal also only in many other cases. For example, so far I only talk about critical NLS, but if you do take supercritical NLS, do a continuation which preserves this time reversibility, you would still have these two properties. If you take, most of the results I showed were for explicit solution, but if you take a non-explicit solution and do a continuation, never mind which preserve this time reversibility, you would still have these two properties. So it's a very general result. What about linear Schrodinger? Can you do the same stuff with linear Schrodinger? Well, there's no collapse in the linear Schrodinger, but you can have collapsing solution if you go to the geometrical optics limit. So let's take this linear NLS here with k0, the wave number, and for simplicity let's take a Gaussian initial condition. If we take the geometrical optics limit, we can solve this explicitly and we get the solution. So now here z is tz, because I need to use here the physical variables, makes more sense. So here is the geometrical optics solution. It's a modulated Gaussian with a function L which is linear in z, which is t. So what is this? We had the initial condition here was a Gaussian which is focused by a lens. The cartoon is here, and therefore the solution under the geometrical optics limit, all the rays collapse at the focal point, and so you have a singularity here. But now, if you have linear Schrodinger with Gaussian initial condition, you can solve this explicitly, not just in the geometrical optics limit, but also for any finite k0. The solution exists globally. And you can take this solution, which I denoted by 5, and then compute the limit of this solution as k naught goes to infinity. If you do this computation, what do you get? Before the singularity, you go to the geometrical optic solution, as expected. After the singularity, you go to the geometrical optic solution, conjugate, but you get some extra jump in the phase, but a finite jump in the phase. So again, you have this symmetry with respect to the singularity. L of z is symmetric, it's linear before and after the singularity. And here you see the cartoon of L of z as k naught goes to infinity. You see that you go to this limit. But if you look on the phase here and you let k goes to infinity, you see that the phase goes to this limit. It's 0 before the singularity. It's minus pi over 2 with some power of times d after the singularity. So there is a phase jump at the singularity, but you don't lose the phase at the singularity. And the reason you don't lose the phase is because the geometrical optic solution, the limit of the phase here does not go to infinity. So there's no reason why you should lose the phase information. So what this shows us is that this loss of phase is a nonlinear phenomenon. Let me show yet another avenue or approach for continuation. And this is based on the vanishing viscosity solutions. Because so far, the continuation I presented were only within the NLS model. We did not add extra terms. Either we played with the initial condition, we play with the power of the initial condition, or we put a hole and so we play with the domain. But let's take the standard approach in conservation laws. Let's add some viscosity type mechanism and let it go to 0. But then the million-dollar question is, what is the viscosity? Which term should we put in that would arrest the collapse, and we would use this, let it go to 0, and use it to continue the solution after the singularity? Well, the thing is to say, well, look on the derivation, right? How you get NLS, for example, in nonlinear optics. You start from Maxwell, so write carefully all the terms that you neglected along the way, and then see which one of them stops the singularity. The problem, there are just too many candidates, and many of them can stop the singularity. Almost all of them, actually. So which one should you choose? It's not clear. And there have been, over the years, various attempts to take these approaches, starting with adding nonlinear saturation or higher order defocusing nonlinearity, and going to some Schrodinger Helmholtz model, and all kinds of approaches of adding terms that would arrest the collapse. And I think what the thing which is common to all these attempts is that they all added sort of viscosities that preserve the Hamiltonian structure. And if you look what's the outcome of all these studies, what can you say with them about the weak solution after the singularity? Not much. So I want to propose a different viscosity, to take nonlinear damping as your viscosity. It has physical motivation. For example, in nonlinear optics, people use nonlinear damping to model the multi-photon absorption that occurs because once the laser beam is becoming, you have collapse, the electric field intensity increases, you start having plasma, the plasma is absorbing the laser beam, it's a nonlinear damping process, and you can model it under some condition with a nonlinear damping. So it's a reasonable physical term. It destroyed the Hamiltonian structure, but this is actually good. So we decided to take a nonlinear damping which has exactly the same exponent as the nonlinearity. So we just add here I delta. This is our nonlinear damping mechanism. So the damping exponent is also critical. What can you say about this equation? Well, rigorously, Antonelli and Sparber show that if delta is greater or equal than 1, no collapse. But if you are willing to live with asymptotics and numerics, you can show that for any delta positive, there's no collapse. And therefore, you can put this delta, let it go to 0, and still you would have global existence. And therefore, you can use this nonlinear damping as your viscosity in order to get the weak solution. So we have done this continuation only in one case. And the case is where the initial condition is again this explicit initial condition. So we take this explicit initial condition, we add this I delta, and we want to compute the limit of the solution. We have global existence for any delta positive. We want to take the limit of delta to 0 and to get the solution beyond the singularity. How do we do it? We use modulation theory. This is based on a systematic derivation of ODEs for the beam width L of t. So it's not a rigorous theory, it's only asymptotic. So here is the idea. You still assume that near the singularity your profile is a modulated R profile. You can show, using this modulation theory, that the reduced equation for L and beta are now here. This is the same equation as before, LTT is minus beta over L cubed. But now here is the effect of the damping. Beta T is minus delta over L squared. You have this ODE system. You can solve it with Airy function. And then you can compute the limit as delta goes to 0 plus. And here is what you get. Before the singularity, the limit of L, as delta goes to 0, goes to this alpha Tc minus T, the width of the initial condition. This is just by continuity. After the singularity, you go again to this alpha T minus Tc, but multiplied by some constant kappa, which is 1.614, whatever. It's not the golden ratio, I checked. It's very close to it, but it's not. So in other words, if you look on the width of the beam, it's asymmetric. It opens in a wider angle exactly by this factor than before the singularity. So you see that this continuation does not have symmetry with respect to the singularity. And the reason is that once you put nonlinear damping, you don't have time reversibility anymore. Going from here in this direction or in this direction is not the same. And that's why even in the limit, the continuation is asymmetric. So here is the summary of the result. Before the singularity, you just by continuity go to the explicit solution. After the singularity, you go to this explicit solution, except you multiply this alpha by kappa, this thing, and you lose also the phase information. For the same reason as before, because this thing is the phase of this cosine. So here are some supporting simulations. Here we plot the width, L, as a function of time, and we vary the value of delta. So here delta is 10 to the minus 5, 10 to the minus 6, 10 to the minus 7. And you see the 10 to the minus 7 is nearly indistinguishable from this triangle, but this triangle is asymmetric. It's Tc minus T here, but it's kappa T minus Tc here. So you really see that the weak limit is asymmetric. Here is the simulation of the phase. we again vary delta in the 5th, 6th, or 7th digit, and we plot the on-axis phase as a function of time, and it has absolutely no effect on the phase before the singularity, but around the singularity it has a huge effect, the variation of delta, and so you lose the phase information after the singularity as delta goes to 0. You can also see it here that as we let delta go to 0, the phase goes to infinity. So in summary, what I presented today are 3 possible continuations of NLS solution beyond the singularity. The first one was based on the idea of Merle. It's a generalization of Merle approach. You take the power just below the threshold for collapse and approach from below. The second approach, which is useful for ring solution, is the shrinking hole continuation. You put a hole, this arrests the collapse, you let the hole size goes to 0. The third approach is motivated by the vanishing viscosity solutions, but here viscosity is nonlinear damping. One of the useful things is that we were able to calculate explicitly the solutions after the singularity, so you can really see how the weak solution looks like. The common thing in all the continuations was that you lose the phase information at the singularity and afterwards. This turns out to be a universal feature. I believe it would hold for any continuation for the reason that the phase at the singularity becomes infinite. The implications of this is that if you have 2 interacting post-collapse beams or filaments or whatever, the interaction within them would become chaotic. You cannot predict whether they would be in phase or out of phase. We saw another property of the continuation, the symmetry with respect to DC, which is a sort of a jump condition. We saw that this holds for all time reversal continuations, but not if the continuation is not time reversal such as nonlinear damping. So it's not a universal feature. So there are all kinds of continuation, but which one is the correct one? And even more fundamentally, is there a correct continuation? Is it true that you can model a laser beam or in BEC a collapsing core after the singularity and use the NLS as your model? Maybe yes, maybe not, maybe sometimes. Maybe there are different physical setups call for different continuations. This is all open. Another question is, what can you say about the properties of these weak solutions? So we saw 2 properties, loss of phase and the symmetry with respect to TC. Are there any other properties? I mean, I look with envy on the theory of conservation laws on weak solutions. We have nothing here in comparison. So this is just, I hope, the beginning of this kind of research. Thank you.